Welcome back to Why Is That Dad? The podcast where I answer my kids' questions by delving into the science, history, and culture behind everything. I'm your host Phil, and with me today, asking the questions is...
Hi, I'm Dominic.
Last time in our series, we discovered the grid's power. We covered the history of electricity and ended in the current war, with the victory of Nikola Tesla's alternating current, which won the day because it could use transformers to step electricity up to high voltage for its long journey. Today, we pick up the story right there. Our winning AC current is surging out of the power plant, usually in a ballpark of 11,000 volts. It stepped up through a transformer to anywhere from 118,000 volts to 765,000 volts, which is pretty insane. Now it has to travel. In this episode, we're going to follow it across the countryside and uncover the history written in its humming wires. We will explore the ingenious physics of high voltage transmission, including the critical skin effect. Discover the historical disasters that shaped the grid, from the paraffin-fueled fires of the Marconi Station to the cascading failure of the 1965 Northeast Blackout, and the material science behind the humming aluminum and steel cables that knit a continent together.
So, Dad, I see those big power lines all the time in the steel towers. They look rather intimidating. But, Dad, I have a question from last time when Annalise was asking the questions. You said they step the voltage way up to send it. But if it's so high voltage, hundreds of thousands of volts, isn't it incredibly dangerous? How does it not just escape into the air or zap everything nearby? Why do birds perch on them? I can't say I've ever seen an electrified bird under the wires. Are they coated in plastic or something? What's up with that, Dad?
Electrified birds? Someone has got to try that for the world's fastest cooked Thanksgiving turkey. Those are good questions, and one that most people wonder at least once, because the answer is the first rule of the electrical highway. Air is an insulator. And when the lines are at least 45 feet above your head, it's a lot of insulation that prevents the electricity from arcing down to the ground. Those massive wires you see carrying 765,000 volts of electricity on the towering steel latticework, they are completely bare. No rubber, no plastic.
They're bare metal. That's kind of terrifying.
It seems it, but really it's just calculated spacing. The wires are hung from the towers by long strips of ceramic or glass discs. Those are the insulators. Their job is to keep the high voltage wire far enough from the grounded metal tower so that the electricity would rather stay on its intended path than jump through the air to the tower. Electricity, like most people, follow the path of least resistance, so they follow the wire because the air has high resistance. This also answers why birds don't turn themselves into a sizzling pile of feathers. Electricity needs a path from a high voltage to a lower voltage, usually the ground. With air as the insulator, a bird with both feet on the same wires is at the same electrical potential. It's like standing on a single step of a ladder. There's no height to fall from, electrically speaking. But if the same bird were to stretch out a wing and touch the metal tower or a different wire at a different voltage, that creates a fatal path. So the birds are safe, but only as long as they mind their wings.
Unlike that squirrel who started munching on peach pits by the transformer by our house.
He was eating peaches off my peach tree, so he had it coming.
But the air doesn't always have the same resistance. What about humid or foggy days?
You've touched on a constant battle engineers fight, corona discharge. On humid days, or especially around high voltage hardware, you might hear that sound, a faint sizzling static. That's corona loss. It's the sound of the incredibly strong electric field at the surface of the wire, literally ripping electrons off of air molecules, ionizing them and creating a tiny glowing plasma. That blue-purple glow you sometimes see around power lines in fog, that's called St. Elmo's fire. It's electricity literally leaking into the air, and it represents wasted energy. Engineers hate it. They use specially designed thick bundled wires to smooth out the electric field and minimize this loss. This fight to contain high voltage has a dramatic, fiery history. In the early 1900s, one of the most advanced electrical facilities in the world was the Marconi Wireless Station in Glace Bay, Nova Scotia. It was built to screen the first radio signals across the Atlantic, which required monstrous, ear-splitting voltages. To store all the energy, they used massive banks of capacitors. Think of them as giant sandwiches of metal foil and glass plates. And to insulate those plates, their engineers used what was, at the time, a standard, paraffin wax.
Wax? Like a candle?
Exactly like a candle, and it had the same fatal flaw. Under that immense electrical stress, the paraffin would chemically break down and release flammable gases. Eventually, the electricity would arc. A massive spark would jump through the wax like a miniature lightning bolt. It was a disaster. The station was plagued by catastrophic fires. Those giant capacitor banks would literally explode in flames, turning the whole building into a tinderbox. They called it the Thunder House for a reason. It was violent, loud, and incredibly dangerous. The Marconi fires were a brutal, expensive lesson. Engineers realized they couldn't rely on organic materials that could melt or burn. This pushed the industry to perfect high-tension porcelain and glass. Those heavy ceramic discs you see dangling from power lines today, they're the direct descendants of those lessons. They don't melt, they don't catch fire, and they can handle the lightning that turned the old stations to ash.
So they're constantly fighting to keep the electricity on the wire. But why do the wires look like braided ropes, not just a solid bar? Why is that, Dad?
Now we get to the first brilliant physics trick of AC transmission, the skin effect. Remember our current is alternating, jiggling back and forth 60 times a second? This rapid reversal creates a magnetic field that pushes on the electrons themselves. The effect? The electrons are forced to travel only on the outer surface, or the skin, of the conductor. At 60 Hz in a thick wire, the very center is completely useless for carrying current.
So the middle of the wire is just dead weight?
For carrying power, yes. That's why transmission lines are never solid copper rods. But this leads to another huge question. What metal should we use? You might think copper, since it's in our house wires, but for the sky highway, we use aluminum.
Why aluminum? Isn't copper a better conductor? Why's that, Dad?
It is. Copper is the gold standard for connectivity, but building a continent-wide grid isn't just about physics. It's about economics, weight, and strength. Copper is dense, heavy, and expensive. At over $5.50 a pound, stringing thousands of miles of solid copper wire would be financially impossible. The towers would have to be massive to hold all that weight. Aluminum is a secret weapon. It has about 60% of the connectivity of copper, which is still excellent, but it's 1/3 the weight and 1/3 the cost. For overhead lines where weight is everything, aluminum wins. A pound of aluminum gives you 3 times the length of the wire as a pound of copper for the same price. You can build farther, higher, and cheaper. But pure aluminum has a fatal flaw. It's weak. Hang it between 2 towers and it would stretch and sag over time. The solution is one of the great partnerships in material sciences, ACSR, or Aluminum Conductor Steel Reinforced Wire.
Steel? But steel's a terrible conductor, right?
It's a terrible conductor for electricity, but a fantastic conductor of force. An ACSR cable has a core of high-strength steel strands. The steel has a tensile strength of up to 200,000 pounds per square inch. It's incredibly strong. Wrapped around the steel skeleton are the aluminum strands. Remember the skin effect? The AC current travels happily in the aluminum skin and completely ignores the non-conductive steel bones. We get the lightweight, conductive properties of aluminum for the electricity and the rugged, high-strength properties of steel to hold the whole thing up over a canyon. It's a perfect marriage of materials. But that marriage has one hidden long-term quirk. Aluminum has a property called creep, or cold flow. Unlike springy steel, if you put aluminum under constant tension for decades, it very slowly, permanently stretches.
So the wire gets longer and saggier forever?
Exactly. It's a microscopic, relentless drift. A line perfectly tensioned in the 1970s might be several feet saggier today. That's why a huge part of grid maintenance isn't fixing breaks, it's called line tightening. Crews have to go out every few decades, loosen the clamps, pull up the slack, and retension everything. It's a silent, slow motion battle against the very metal we chose.
But I thought the steel core prevented it from sagging.
It prevents it from catastrophic sag, but the aluminum is still undergoing a very slow motion stretch over the decades.
Okay, I don't know if this is related, but I have a memory. We were walking near Uncle Francis's house, right under those big lines. There was this heavy, constant hum. It wasn't a buzz, it was in the air. What was that?
That's the iconic sound of the grid itself. That deep 60 hertz, or really 120 hertz in this instance, hum is primarily magnetostriction. Inside the big transformers at substations and in the steel of the towers themselves, the alternating magnetic field from the AC current physically squeezes and stretches the iron, or steel molecules, 120 times a second. The metal itself is vibrating microscopically, and that vibration couples into the massive structures, making them sing. It's the sound of the magnetic field doing work on metal. On a quiet day, it's the audible heartbeat of our civilization.
That's amazing! And the wires always sag in that long, lazy U-shape between towers. They don't pull them tight.
That curve is called a catenary curve, the natural shape a flexible cable takes under its own weight. They can't pull it tight like a guitar string. In winter, the metal contracts and would snap. In summer, it expands and would sag too low. They calculate the sag perfectly so it's safe in all seasons. It's a balance between gravity, tension, and temperature. But engineers have to plan for much wilder forces than just the heat and cold. One of the most dramatic is called galloping.
Galloping? Like a horse?
Exactly. Under just the right or the wrong conditions, a power line can start to buck and wave like a rodeo bull. It happens when a wire gets coated in a perfect sleeve of ice, and then a crosswind hits it. The ice changes the wire shape. The wind gets underneath and starts to lift it rhythmically. The wire can enter these massive traveling waves that are 20 or 30 feet high. It looks terrifying. It can cause the lines to smash together, creating huge short circuits or rip the hardware right off the towers. To stop it, engineers attach strange devices to the lines like Stockbridge dampers. They look like weighted dog bones to absorb the energy and spiral spoilers to break up the wind. It's a full-on physics battle against the weather. Keeping the wires up is one thing. Keeping the power flowing is another. And it requires a feat of coordination more precise than any ballet. Every single generator on the entire eastern North American grid, thousands of them, must spin in perfect lockstep at exactly 60 hertz. And this is called synchronization.
What happens if one starts to spin a tiny bit slower?
If a generator lags even a fraction of a hertz behind, it stops being a source of power. It becomes a load, like a giant motor, trying to drag the entire continent's grid down with it. This was understood from the very beginning. One of the first great tests was in 1891 at an exhibition in Frankfurt, Germany. An engineer named Mikhail Dobrovolsky had to keep a generator at a waterfall and a motor 109 miles away in perfect sync. His success with three-phase AC proved the synchronized grid over long distances was possible. It's why we use three-phase power today. Today, grid operators watch this sync in real time on systems called SCADA, S-C-A-D-A. They monitor the phase angle between, say, Chicago and Cleveland. If that angle starts to drift, it's a 5-alarm warning. They have minutes, sometimes seconds, to shut off power to some areas or fire up more plants to rebalance the system. It's a high wire act conducted at the speed of light. The consequence of losing that synchronization was learned in the most dramatic way possible. On November 9, 1965, at 5:16 p.m., the entire Northeast learned this lesson. It was an ordinary evening. At a hydroelectric plant on a Niagara River in Ontario, a single, small, protective relay, a device meant to save equipment from a power surge, had been set too sensitively.
One little switch?
One little switch, doing its job wrong, and misinterpreted a normal power flow as a dangerous surge and tripped, shutting down a key transmission line. In that perfectly synchronized grid, the power had to go somewhere else instantly. It flooded onto neighboring lines, overloading them, causing their relays to trip. It was a cascade of failures, like dominoes falling across the Northeast. Within 12 minutes, over 30 million people across New York, Ontario, New England, and New Jersey were in a blackout. New York City went dark. People were stuck in elevators, subways, and skyscrapers. The event proved that in a connected grid, a fault in Canada could plunge New York City into darkness. There was no malice, no storm, just a tiny engineering miscalculation that revealed the profound fragility of the system. The investigation that followed was massive. It led to the creation of strict national grid standards, regional reliability councils to coordinate in real time, and much smarter computerized controls. The modern smart grid, with its constant monitoring and automated response, is a child of the Great Blackout of '65. We built a more resilient highway because we saw what happened when one pothole could collapse the entire bridge.
It's hard to believe that all of these different states are connected. Maine to New Jersey? Hard to believe that people in Maine would allow anything from New Jersey to contaminate their beautiful state. Their dirty politics, dirty air, dirty beaches. But I digress. That must span hundreds of miles.
Hey, this isn't a political podcast. Keep it civil. New Jersey has beautiful areas too. I love hiking the Delaware Water Gap and High Point. It's gorgeous. But back to the grid. To grasp the sheer scale of this highway, consider the numbers. This isn't just a Maine to New Jersey thing. In the United States alone, there are over 200,000 miles of high voltage transmission lines. That's enough to wrap around the Earth's equator 8 times. This doesn't even include the millions more miles of lower voltage distribution lines on neighborhood poles This network forms three major interconnections: the Eastern Interconnect, the Western Interconnect, and the Texas Interconnect, called ERCOT. Each is a synchronized machine where thousands of generators spin in perfect unison, balancing supply and demand across millions of square miles in real time. It is, without exaggeration, the largest and most complex machine ever built by humans.
No, it's not. I think that award would go to the Large Hadron Collider in Geneva, Switzerland.
Touche, but the grid is larger. Let's call a draw.
Let's let the audience decide. Post in the comments. What's the most complex machine ever made by man?
So, the whole episode so far is focused on AC, which may have led some to believe DC for transmission has gone the way of the dodo. But here's a fascinating modern twist. We said AC won the war for the main grid, but for the absolute longest distances, engineers sometimes go back to direct current.
What? Back to Edison's DC? Why is that, Dad?
For very specific jobs, DC has a secret weapon. With high voltage direct current, or HVDC, you don't have the skin effect or the constant charging losses that AC has over thousands of miles. For a 500-mile undersea cable to an offshore wind farm, or a 1,500-mile overhead line across a desert, high voltage DC can be more efficient. The catch, you can't use simple transformers. So at each end of an HVDC line, you need a massive conversion station, a building the size of a football field, filled with banks of semiconductors to convert AC to super high voltage DC for the journey, and then back again. It's incredibly expensive, but worth it for the distance. Lines like the Pacific DC Entergy have carried power from Oregon to Los Angeles since 1970. It's a quiet acknowledgement that while AC runs the show, DC still has a critical long-distance role to play.
This all seems so optimized. Every detail has a reason, but it ends at a big fenced-off station with transformers, right? Then what?
That's the substation, the interchange of the electrical highway. Here, massive transformers step down the voltage from transmission levels, like the 765,000 volts, which is a fun number to say, to distribution levels like 13,800 volts. From here, the power branches out into the smaller wooden poles you see on your street, the distribution lines. And on those poles, you'll see a gray cylindrical can.
The transformer! The one that looks like a trash can on a pole.
That's the final step. The distribution transformer takes the 13,800 volts and steps it down to 120 to 240 volts that safely enters our home. Without that final step, your toaster wouldn't toast. It would vaporize. So the journey is power plant, to transmission lines, to substation, to distribution lines, to pole transformers, and then your house. Let's see what our listeners learned about the electrical highway and its dramatic history.
That means it's trivia time! If you know the answer, make your pet parrot remember the answer so they can squawk the answer ad nauseum so you'll never forget. What property of aluminum means power lines slowly get saggier over decades, requiring line tightening? What 1965 event, starred by a single misset relay, proved the fragility of the interconnected grid? And for ultra-long distance power lines, what technology is sometimes used instead of AC for greater efficiency?
In our next and final episode of this series, we'll follow the electricity inside our walls. We'll explore the invisible river, safety, meters, and the future of power. We'll explain GFCIs, breakers, how your meter works, and where solar panels and electric cars fit into this ancient grid. If you're finding this journey illuminating, please subscribe. And if you can, leave a 5-star review. It's the best way to support the show. And take a look at our YouTube channel, Contemplative Chaos.
Thanks for traveling the electrical highway with us. Keep asking, why's that?
See you next time. God bless.